Well, hello friends, welcome back to OS Hacking. Today we are going to deal with a thing that I've been postponing for a long time, and it's out of memory conditions. So currently, let me show you what happens if we allocate 300 megabytes from user space. Everything has just frozen and we are totally dead. And then if you look here, we can see that we have an insertion failure in the kernel memory manager allocate user physical page, because if we run out of memory, we just say, oh, I don't know how to deal with this situation. So that's not super great. So what we're gonna do today is we're not gonna build the most magical solution, but we are going to at least make us handle this situation a little bit better by at least crashing, like whoever is trying to allocate memory when this happens. So like whoever tries to allocate memory at the moment when we run out, you're out of luck and we're gonna kill you. And then we can, once we get that out of the way, we can start thinking about more sophisticated approaches to avoiding getting there in the first place. But I think today we're gonna have to just deal with this initial stop freezing the whole, or panicking like the whole kernel thing. So if we look at, actually let's look at the stack here. So we are dying in memory manager allocate physical page, and if you look at the stack trace here, you'll see that this is in response to a page fault. So we have a page fault somewhere in user space, and it's a zero fault, which means that it's just a piece of memory that we told the process that sure, you can have this memory, but we didn't actually allocate any physical memory or physical RAM for it yet. And then when we get the page fault like we do now, we're supposed to go and fetch some physical RAM, but we run out. So that's what we're dying on. And that's what a zero fault does. It just takes care of those IOUs that you've been handing out when somebody comes to collect on them. So handle zero fault. So we'll be here, right? So if we look at this call here to allocate physical page, we should handle the scenario where the page is null, because then we'll just say, oh, handle zero fault was unable to allocate a physical page, and then we will crash the process. But we never even get here because we assert in here. So we're asserting on line 451. All right, so that's right here. Okay, so when we do run out of memory, before we give up, we will go over all of the purgeable memory that we have in the system and figure out if we have any volatile purgeable pages. And if we do, then we will purge that memory, like reclaim it for the kernel, and then give you something that we just purged. So we can actually see here that purge saved the day. That means that twice we were able to recover from this situation, actually using the same VM object. But we were able to recover from this situation twice. And that was a good thing, but obviously wasn't enough to save us if we just keep putting pressure on the kernel. So here, instead of asserting that we found a free page, we'll just allow it to fail and then break this iteration, and then we should fail down here instead, but let's verify that. So we should assert on line 459, and we are asserting on line 459, and then let's just let him slip through as well. So we run out of physical pages, and then we'll tell the process, okay, well, you go and die now. And then what happens? Okay, well, we're still frozen or panicked. Okay, so now we are failing. We have a write page fault in the kernel's hard drive. Device driver code. So I'm guessing that somebody in the kernel caused this and doesn't check for an error. Where would that be? That's probably this one. Is this one? Commit was unable to allocate a physical page. Right. So commit, you can call commit on a memory region, which we do in a bunch of places. And what that does is instead of having the physical memory lazily allocated, when we commit a region, we just allocate all of the physical pages needed up front. So after you committed a region, it has no unallocated physical page slots. That's the point of commit. And here we'll return false, but I bet you that nobody checks that. Yeah, people are very, very bad about checking that. Look at this guy. This guy can't even fail if commit fails. What do we have here? Allocate region, can't fail. Well, we should teach it how to fail, but it doesn't currently fail. Profiling code doesn't know what to do if it fails. Okay, so we got a lot of people who don't handle failure gracefully. So I think the thing that we're going to do right now is we're just gonna assert here. So we're sort of moving that problem a little bit, and then we'll see who is trying to commit something and see if we can avoid that. So, okay. So now we are asserting in commit and allocate kernel region elf loader symbolicate in crash. Okay, so now what's happening is our allocate program is crashing, right? Because the page fault handler said, hey, you should crash. And then that actually propagates all the way to process crash, which is great. But then we're trying to symbolicate the process to generate a backtrace. And in the process of trying to fetch the symbol table, we try to allocate memory, which we're just fresh out of. So I think in this scenario, we're going to have to have a special, there's some way to communicate to the crash code that we don't have memory, so don't go trying to do anything heavy. Like, you can't allocate. And normally nobody does that during crash, I think. Or maybe this is the part where we learn that crash is actually really allocation heavy. Because, I mean, allocation, like kernel heap allocation is fine, because that comes out of the kmalloc heap. Slab allocation is fine. What you can't do is you can't allocate like a discrete physical page. So we can't incur a page fault at this point, for example, or at least not one that would need to allocate memory. But essentially, we want to get rid of dump backtrace here. And I think that will basically do it. So let's just see if we comment that out, what will happen. Because if nobody does backtraces, will that just solve our problem? Okay. We're trying. Oh wait, hold on. We're still trying to symbolicate something. We have to skip that as well. So we can't symbolicate the current address either. Oh, I didn't do that correctly. Okay. Make and sync and run. And look at that. Okay, so we have survived this horrible situation. You can see that spike coming up there. It didn't. I guess we didn't even make it far enough, fast enough for the program here to be able to notice what was going on. Now you can see it spike up a little farther. But basically, we're able to survive the situation now if we just avoid symbolicating. So what we want to do is we want to communicate from the page allocation failure in the virtual memory manager to the crash handler that we are running under like special OOM, like out of memory crash conditions. So how do we do that? Let's go and look at how do we do should crash. That was the one that we were sending in the zero fault. So here, for example, we say should crash, and that is one possible page fault response. Really, there are two possible page fault responses because some page faults we can manage, right? Like if you get a cow fault, for example, so you've been sharing memory with another process and it's copy on write, and then you try to write to it, then we page fault, but then we give you your own private copy of that memory, and then we continue executing you, and you're none the wiser. That's what the continue page fault response is for. But for the should crash, here's what we do. So in the page fault handler, like this is where we actually handle the raw CPU exception comes in here. Or I guess technically it comes in here, but in C++ terms, we come in here. And we call the page fault handling code here. So we call handle page fault, and then we look at the response. And then we get should crash. I'm thinking this would be maybe a good place to have like a separate mode, like should crash, or response is page fault response should crash or like out of memory. Out of memory. I mean, that's not like, it's not a page fault response. It's more like, but maybe that's okay. Should crash out of memory. I mean, I was thinking of page fault response as like, what is our response to this page fault? But you could also think of it as like, what is the response from the page fault handler? It's like a tiny, stupid little detail, and it probably doesn't matter in this context because this code reads pretty understandably. So let me switch my editor over to kernel, actually. So here, basically, if we are out of memory, we still want to print out some stuff, although I think we don't care about giving you a sev handler at this point. So we'll only do this if it's not out of memory, I think, because you're just fresh out of luck. Can't handle that seg fault. And here, handle crash. This is where we would start to symbolicate and stuff. So we'll have to plumb this through a little bit. Handle crash, and maybe we will put a little boolean here, like is out of, or just out of memory. False. Out of memory. Out of memory. Okay, and then we're calling this in a bunch of places. And here we will say that we'll say out of memory if the response is page fault response out of memory. Okay, and then we just have to teach a bunch of places to return this particular response. So let's see. Basically anywhere that we fail to allocate, right? So not here, but here. Unable to allocate a physical page. This is actually structured a little weird, the inode fault handler. I'm not a huge fan of the way we do this, because we like disable and re-enable interrupts a few times and stuff, and it's kind of interleaved, and it's very probably racy, or it is racy, and I don't like it. But I was just thinking, we do the actual page allocation so late here, even after we've actually read from disk, then we allocate a page. Like, you could allocate the page sooner, I think, but anyway, I don't want to mess with that right now because I'm sure that will break something. Probably if you have a shared inode VM object that's used by multiple processes, and then you have a race because you fault the same page in two processes, and something would go wrong if we change the order. So we're not here to mess with that. But if we fail, we should say out of memory. Okay, then we'll do the same in the cow fault. So if we have to copy and write, but we can't allocate, out of memory. And the same in the zero fault. So here we'll say out of memory. Okay, and this is looking kind of reasonable-ish. Okay, so we forgot about that process change. Crash. Oh, out of memory, false. So who else calls this, by the way? Only one place calls it. Okay, then we don't have to have a default param. And we can go and actually edit the code. So bool out of memory. Okay, something like that. And then if we are out of memory, then what we'll do is kill this. Out of memory, killing, yeah. Basically. Oh shit, were we actually doing this in more places? I just didn't realize. Yes. Alright. Alright. We'll have the thing. I think this will be pretty good. I mean, it's not great, right? But it is better than panicking the kernel and freezing the system. And you can't do everything at once. You gotta take steps. And this is a step towards better life on Serenity. So now we can spike up the memory, and by the time it gets to the top there, then we recover. So what happens? Can we, let's see. It's too fast, like we don't even see the graph shooting up. Can we slow that down a bit maybe? The allocate program, how do we do that? Do you sleep? Seems like he doesn't sleep in between mallocs. just do something small like that, sleep 1 millisecond or 10 milliseconds, whatever. I just would like to see it like go up a little bit slower. Maybe that was too slow. See, now we can at least see it going up, although it's way too slow. I just want to see it going up in a cool, slow way. Okay, that's pretty good. So, can we do this? Yeah, so memory usage starts to spike. Interesting. And what do we say in the kernel log? We log the memory layout of the dead program. Crash, blah, blah, blah. Do we actually say? Yes, here, out of memory, killing. Okay. Maybe we should make that like obnoxiously loud. No, not here. Here. So we'll do something like this. Okay. That's pretty okay. Okay, so let's commit some stuff. So what do we have? We have the crash changes. We added the out of memory thing. And we stopped. So I guess we can do this one first. Just stop asserting that allocate user physical page succeeds, because now it can fail. Don't assert in allocate, assert in allocate user physical page. Instead, we now give callers a chance to react to situations. Okay, and then let's do the region commit thing, which was, how did we deal with that? Just so we assert, right? Yeah, here. We assert if region commit fails to allocate a physical page, because I don't want to deal with that particular situation right now. Yes. No, 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 no. Wait. Yes, no, no, no. Okay. Kernel. Assert in region commit. There are two. A lot of this function has a lot of callers that don't bother checking the return, checking if it returns success or not. We'll need to handle failure in a bunch of places, and then we can remove this assertion. Okay, and then then it's just about handling crash and communicating that it's an crash. So what do we say about this? Handle crash the current process on instead of panicking kernel. Now this patch adds a page fault response out of memory, which informs the CPU exception handler that, fault exception handler that, or a fault exception, that sounds like I shouldn't say both of those things. Fault handler informs the fault handler, yeah, that we were unable to allocate a necessary physical page and cannot continue. In response to this, kernel will crash the current process to avoid, or because we are in because we are we can't symbolicate symbolicate the crash like we normally would, so we also communicate to process crash that we're out of memory. Since the symbolication code would want to allocate. Symbolication code needs to allocate. But now we can survive. Allocate 300 megs. What happens if we allocate way more? Probably the same thing should happen, but let's try it anyway. Oh, you can't do that? It doesn't support gigabytes. It's not very ambitious. So that just failed right away. Why did that fail right away? I feel like that's not the same failure that we saw before. Okay, I don't know what's up with those, but those are not the crashes that I'm looking for. This is an out-of-memory crash. Yep. Unrecoverable page fault. No, okay. So yeah, I guess that's it basically. Only the allocate process dies. This is definitely not perfect and can easily end up killing an random innocent other process who happen to allocate allocate one page at the wrong time, but it's a lot better than panicking on oom. Okay, so that's that. I've been meaning to do this for a long time, and in the future, I mean, I think we're going to be done with hacking for today, but just wanted to talk about the future a little bit. So in the future, we're going to want to be maybe dividing this logic into a synchronous component and an asynchronous component. And this sort of the synchronous component is the some code that runs an urgent response to like a condition in a page fault scenario, right? Which is what we have right now. Like we need a page of memory and we can't continue without one. Then we need to do something synchronously to be able to continue. And this is one thing that we can do. Another thing we might want to do in the future is figure out a way to block the current process for a moment and then let a kernel task come and just pick someone else to kill, potentially, like choose the correct thing to kill based on some heuristics. And that's some more sort of a hybrid between synchronous and asynchronous, because you will block the page fault handling until a helper task can free up some memory. And then in addition to that, I would also like to do some sort of asynchronous thing where we have an independent thing that runs periodically in the kernel and just monitors the system and maybe notices that some process is sort of out of the normal range of where he should be memory-wise. Like if something is getting suspiciously large, it would then inform that process somehow, hey, dude, you're getting a little big there. Don't you want to do something about that? And then give that process a chance to shrink down. And if it doesn't shrink down below some reasonable limit, we could then, take some executive action, right, and kill it. And I think a combination of synchronous and asynchronous response to this sort of stuff is where we'll eventually want to go. But today I just wanted to get the very first baseline synchronous response to oom, which is to just kill whoever is current when we oom so that we don't panic the kernel. And now we can do that, so mission accomplished. Anyway, like I said, that's going to be it for today's video. So if you made it this far, then I thank you for watching and for hanging out. I hope that you saw something interesting today, and I guess I'll hope to see you next time. Bye.